Hello everyone, welcome back to the videos, and we're gonna continue with the recitation videos, and specifically we're gonna focus on the surface area. Okay, and again, uh, if you have some curve, and you're spinning the curve around the x-axis, then the surface areas for the solid obtained when you're rotating the curve around the x-axis is given by these two formulation. And again, I would say that these two formulation are equivalent. It's just different because of the setup. I mean, if you set up the integration in both way, they should give you the same numbers. But if the question describes the curve as a function in terms of x, and then you're gonna use this formulation. If the question describes the curve as a function in terms of y, then you're gonna use this formulation. But these two are equivalent, and this is the integrations where you have the rotations about the x-axis. If you have the rotation about the y-axis, then you can use the same ideas of discretization to come up with the integration that represent for the surface area. And in these videos, I just focus on the way on how we use these formulation to help us compute the surface area. If you want to have the better explanation why we have these formulations, you can go back to the lectures videos, and from that videos you will have the better understanding how can we derive these integration to compute the surface area. Okay, in this problem you have the curve x cubed. Okay, you have the curve x cubed, and you rotate the curve about the x-axis. Okay, you rotate the curve about the x-axis. And the question wants you to find the surface areas for the solid that you obtain when you're spinning the curve about the x-axis. Okay, the question wants you to find the solid, the surface area. So from here, firstly, you have to determine that you have something spinning around the x-axis. So you're gonna use one of these two formulations. The second thing is this function is described. I mean, the curve is described as a function in terms of x. So you're gonna use the first one. Okay. So from here, let me copy down the first one. And from here, you have to see that if you want to use this formulation, you have to know the lower bound and the upper bound. So from here, the lower bound is 1, the upper bound is 2. The function that you have, this is f of x. Okay, this is f of x. And you need to figure out f primes of x squared as well. So f primes of x will be 3x squared. Therefore, f primes of x squared will be 9x to the power of 4. Okay, so from here, you can set up your integration. You have the integration from 1 to 2. Let me take 2 pi outside. Okay, just constant. The integration of the function f is x cubed. So I have x cubed. The square root of 1 plus f primes of x squared. Therefore, I have 1 plus 9x to the power of 4. The x, okay, and I believe you should be familiar to this one because you see that you have the function composition. You have some function inside a function, and you have some extra functions over here. And the point is, when you take the derivative of the inner function, you will have something that's proportional to x cubed because this is x to the power of 4. Okay, so set up u equal to 1 plus 9x to the power of 4. Therefore, du will be 36x cubed. Okay, and the thing is, you have x cubed dx. Okay, therefore, du divided by 36 is x cubed dx. Okay, And remember that when you do the substitution, you have to update the bound as well. So to update the bound, I will create a table of values. The first row is for values of x. X is from 1 to 2. Now I need to figure out the bound for u because I'm gonna translate the entire integration into the integration in terms of u. Okay, and when x is 1, I have 1 plus 9 times 1 to the power of 4, so I have 10. When x is 2, 2 to the power of 4 is 16. Okay, 2 to the power of 4 is 16. 16 times 9, so I'm gonna have 9 times 6 is 4, so 144. Okay, 144 plus 1, I have 145. Okay, and now I'm gonna have integration 2 pi 10 145 x cubed dx is du divided by 36. Okay, and the square root of 1 plus 9 x to the power of 4 is just square root of u. Okay, and I can bring 1 over 36 outside. I have 2 pi over 36. I have the integration, the square root of u is u to the power of 3 half divided by 3 half. The bound is from 10 to 145. And then you have pi over 18. You just need to plug in the upper bound and lower bound. From over here, if I plug in the bound, the number is kind of ugly because I cannot take the square root of 145 and square root of 10, and then I have to rise to the power of 3. But for the original problems, I believe the numbers that you have will be much better. Okay, so I just leave the final result as something blank over here, but I would say that the idea is straightforward. You just need to plug the upper bound and plug in the lower bound. You find a difference, then you will have the final number, and that number is represented for the surface area of the solid that you obtain when you're spinning the curve around the x-axis. Uh, and for problem 7, firstly, you have to see this one. Let me adjust the questions a little bit. I have, let me suppose I have x cubed. Okay, let me suppose I have x cubed. So when I have x cubed, the point is over here, you are spinning the curve about the y-axis. Okay, you are spinning the curve about the y-axis. So you have to figure out that when you're spinning things about the y-axis, then you're gonna use one of these two formulation. Okay, and over here, because the question give you the setup, such as you are describing the curve as a function in terms of x, so I'm gonna use the first one. Okay, I'm gonna use the first one. Okay. Okay, and then let me do the manual calculation so that I can have the better questions. X squared, 3x squared, square root 9x to the power of 4. Let me use 2x squared, for instance. Okay, I use the function 2x squared. Okay, Okay, and again, you have the function in terms of x, and you're spinning that functions about the y-axis. And the question wants you to find the surface areas of the solid that is obtained when you're spinning these things about the y-axis. Okay, so again, this is the function f of x. F of x is 2x squared. So f primes of x will be 4x. Okay, and you need to figure out f primes of x squared. So f primes of x squared is 16x squared. Okay, now my integrations is from 0 to 1. Okay, from 0 to 1, 0 to 1. Let me take 2 pi outside. I have the integrations of x times the square root of 1 plus f primes of x squared, and f primes of x squared is 16x squared. Therefore, I have 2 pi 0 to 1. Okay, and I mean, again, I would say that this integration is perfect for u substitutions, because if you set up the inner function as u, when you take derivative of u, you will have something that's proportional to x dx. Okay, set up u equal to 1 plus 16x squared. Therefore, du will be 32x dx. And in your original integration x dx, you have the extra things as x dx. So I will divide both sides by 32 so that I can rewrite x dx as something in terms of du. X dx as something in terms of du. Okay, now when you do this u substitution method, remember that you need to update the bound as well. So to update the bound, I will create a table of values. The first row is the values for x. X is from 0 to 1. And now you need to compute the values for u. So when x is 0, the corresponding values for u will be 1 plus 16 times 0 squared, which is 1. When you have 1, plug in over here, you have 1 plus 16x squared. 16 times 1 squared is 16. Saying 16 plus 1 is 17. So you have 17. Okay, therefore your integration become 2 pi, the integration from 1 to 17, square root of u du divided by 32. Okay, u is 1 plus 16x squared, so you have square root of u. Okay, and x dx is du divided by 32. And from here, I believe that thing is become straightforward. You can take out 32 because it's just constant. You focus on the integration of square root of u. And again, you can use the power rule. You're going to have 2 pi over 32 u to the power of 3 half divided by 3 half from 1 to 17. Okay. And you plug in the lower bound, you plug in the upper bound. You find a difference. The final numbers will be the surface areas. I will leave that for you to do. Now, the questions want you to find the surface areas of the volume generated by the curve when you're spinning this thing about the x-axis. Again, you have something, you have the curve. The curve is described as the function in terms of x, and you're spinning this thing about the x-axis. So you're going to use, firstly, you're spinning something about the x-axis, and your function is in terms of x. So again, I will use these transformations. Okay. Okay, and my function f of x is square root 9 minus x squared. Therefore, f primes of x will be 1 over 2 square root of 9 minus x squared time 9 minus x squared prime because of the chain rule. I mean, if you have square root of u, you take derivative, you're going to have 1 over 2 square root of u, but you need to involve the chain rule. So you need to multiply your derivative with u prime. Okay? 1 over 2 square root of u times u prime. Okay? Okay, let's simplify this one. We have negative 2x divided by 2 square root 9 minus x squared, or you have negative 1 over square root 9 minus x squared. And because you need to find f primes of x squared, therefore you're going to have 1 over 9 minus x squared. Okay, you square this thing, so negative 1 squared gives you 1 square root 9 minus x squared, and you square it, you get a square root. Okay, now let's simplify the thing that we have. You have the integration from the lower bound to the upper bound. So you have the integration from 0 to 3. I take 2 pi outside. My function f of x is 9 minus the square root of 9 minus x squared. So I have 9 minus x squared into the square root. For the other square root, I have square 1 plus f primes of x squared, and f primes of x squared is 1 over 9 minus x squared dx. Okay. So you're gonna combine these two things. I'm sorry, I have a bit of mistake over here. This is negative x because you just cancel out 2. Okay, so you still have negative x. And when you square it, you will have x squared. Okay, you will have x squared. So up here, you will have x squared. Okay, and now you combine them together. I mean, you have square root of something times square root of something. If you have square root of a times square root of b, then you can rewrite this as square root of a times b. So I will combine these two square root. I have 9 minus x squared times 1 plus x squared, 9 minus x squared dx. Okay, and the point is 2 pi 0, 3. 9 minus x squared times 1 give me 9 minus x squared. Okay, and 9 minus x squared multiply with this fraction. 9 minus x squared will cancel out 9 minus x squared, and we'll have just plus x squared. Okay, x squared and x squared cancel out. You just have the square root of 9, and the square root of 9 is just 3. So you have 2 pi, the integration 3 dx, and you have 2 pi 3x 0, 3. You plug in the upper bound, you plug in the lower bound, then you're going to have 2 pi times 9, which is 18 pi. So this is the surface areas for the solid that you obtain from spinning this curve about the x-axis. Okay, so we're done with the surface areas, and if you want to have more practice, you can go to the textbook that I attach on my syllabus, and you can find more problem to practice with the surface area topics. In the next recitation video, we're going to talk about the other applications of integration, which is mass and work, force work. Okay, so I will see you in the next videos.